The transition from an extraction-based economy to a creation-based economy represents the most significant industrial shift in human history. For over a century, we have relied on the Haber-Bosch process to create the synthetic fertilizers that keep billions of people alive. This process is essentially a brute force approach to chemistry, requiring massive amounts of heat and pressure to break the strong triple bonds of nitrogen molecules. It consumes nearly 2% of the world's total energy and is responsible for a massive share of global carbon emissions. Yet, in nature, a tiny bacterium living in the roots of a clover plant performs this exact same task at room temperature and normal pressure, using almost no energy. This is the nitrogen fixing paradox. The reason we cannot replicate it is that the molecular mechanics of the enzyme involved, nitrogenase, are too complex for our current computers to simulate. We are currently entering the era of the synthetic leaf and quantum chemistry, where we stop guessing at molecular structures and start architecting them with subatomic precision. To understand the challenge of traditional chemistry, you have to look at the many-body problem. In a classical computer, calculating the interaction of every electron in a complex molecule is a mathematical nightmare. Electrons are quantum particles. They exist in superpositions and are entangled with one another. A classical computer tries to track each one individually, which causes the required memory to double with every electron added. This is why we can't perfectly simulate even simple biological catalysts. Quantum computers, however, use qubits that operate on the same rules as the electrons themselves. A quantum computer doesn't simulate the molecule, it emulates it. By mapping the quantum states of the target molecule directly onto the qubits of the processor, we can find the ground state, the lowest energy configuration of complex enzymes and catalysts. This capability allows us to solve the Haber-Bosch problem by designing a synthetic catalyst that mimics the efficiency of nature. We are architecting a synthetic leaf, a material that can pull nitrogen or carbon dioxide directly from the atmosphere and convert it into fuel or fertilizer with nearly 100% efficiency, using only sunlight as an energy source. This is the end of the industrial age as we know it. We are moving away from a world where we build massive polluting factories to force chemistry to happen, and toward a world where we design materials that perform that chemistry naturally. For an engineer or a technology founder, this is the ultimate clean tech frontier. It's the ability to solve the climate crisis not through austerity, but through superior subatomic design. The implications extend to every industry that relies on advanced materials. We are using quantum simulations to design solid-state batteries that can charge in minutes and hold 10 times the energy density of current lithium-ion cells. We are architecting room-temperature superconductors that will allow for frictionless power grids and ultra-fast maglev trains. We are even designing smart materials that can change their physical properties, such as strength, conductivity, or transparency, in response to a subatomic trigger. This is molecular engineering in its purest form. We are moving from being observers of matter to being the master builders of it. For a veteran or a security professional, the move to a quantum-designed material world is a matter of strategic resilience. A nation that can create its own fertilizer and fuel from thin air is a nation that cannot be held hostage by global supply chains or energy blockades. It represents a total decoupling from the resource scarcity model of the 20th century. This is energy sovereignty through quantum overmatch. As we move through the next decade, the primary metric of national power will shift from oil reserves to simulated qubit capacity. The first nations to master the synthetic leaf won't just solve their own energy problems. They will own the blueprint for the next 1,000 years of human civilization. We are finally learning how to play by the same rules as the universe. And in doing so, we are unlocking the ability to create a post-scarcity world.